Hey everyone, in this video we'll build and train a simple neural network using TensorFlow. I already prepared the code to do this beforehand in my Jupyter notebook here, so I'll just be explaining what every cell does as we run it. Before we build our network though, we'll need to prepare the data we'll use to train our model. The model we'll build will be a simple model that predicts whether a given client is eligible for a loan given their monthly income and their credit score. This is a simple made-up problem, and please note that we won't be using any real data in this video, but everything we'll learn works just as well with real data. Now what we're doing in the first cell is importing all the libraries we'll use. In the first section we import numpy and the randint function from random. We'll also bring in the min-max scaler, which we'll use to pre-process our data before training our model. And to build our model, we'll use sequential from keras.models and the dense function from keras.layers.core for building our layers. We'll also bring in activation from keras.layers for our activation functions. And in the last section, we bring in atom from keras.optimizers and categorical cross entropy from keras.metrics, and these will be used when training our model. In this cell we declare two arrays, one for our samples and the other for the labels. Remember we said that training data is labeled. Now to generate the fake data we'll use, I'll be populating our samples and labels arrays through these loops. The first loop will run 1,000 times and it will first generate a random income between 5,000 and 50,000. We'll also pick a credit score between 300 and 669. For example, people earning at this rate and these credit scores will not be eligible for a loan. So to samples we append an array of the income and credit scores, and to labels we append 0. In the second section of this loop we do the same thing with the same income but higher credit scores, and these people will be eligible, so we append 1 to the labels. And in the third section we have a higher income between 50,000 and 100,000, and with a low credit score these people will not be eligible, so we append 0 to the label. And the last section has high income and high credit scores, so we append 1 to the labels. The second loop here adds 50 people with high incomes but low credit scores that were considered eligible, so we append 1 to their labels. And the last for loop runs 10 times. In its first section, it adds people with low income and low credit scores that were eligible, and the second section is low income and high credit score clients that were not eligible, while the last section is high income and high credit score clients who were found not eligible. And obviously we'll have fewer clients in these three last sections, so the loop only runs 10 times. In the next cell we convert our samples and labels into numpy arrays. This is because this is the data type that TensorFlow expects our training data to be in, and since our samples have two variables in each sample, we'll reshape the numpy array to contain arrays of size 2. We'll print our samples here to visualize what the data looks like, and we'll see that it's a numpy array with arrays of size 2 in it. In the next cell we scale our training data to values that are between 0 and 1 using the min-max scaler. This is because neural network models usually converge to a solution much easier when dealing with values between 0 and 1. So this is what our samples now look like. Now that we're done preparing the training data, we'll now build this model, which has 5 layers with 2 nodes in the input layer since our data has 2 input values, and 16 nodes in each of the hidden layers, and 2 nodes in the output layer that will classify our data into eligible and not eligible categories. This structure is the one I'll be using, but feel free to experiment with different structures for your neural network. Now to build the model we call the sequential function, which takes to its constructor an array that contains a linear stack of layers. To build these layers we will use the dense function. For our first layer we have 16 nodes and we pass to it an input shape which is equal to 2. This input shape describes our first layer which has 2 nodes, so the 16 nodes belong to the second layer, and we'll give it an activation function of relu. On our third and fourth hidden layers we also have 16 nodes, and we'll use the relu activation function, so they're created using these 2 dense function calls. Our output layer has these 2 nodes and uses softmax as its activation function. We'll run the summary method on our model to visualize our model and see that it has 626 trainable parameters. In this cell, we'll run the compile method on our model to compile it, and to it we pass Adam as our optimizer, and Adam is a variation of stochastic gradient descent that usually converges faster to a solution than vanilla SGD. Adam is short for adaptive moment estimation, and we'll take a look at it and other types of optimizers in a future video, but for now we'll be using it as our optimizer. Now in our Adam function we pass 0.0001 as our learning rate. Remember that the larger the learning rate, the more quickly the model will converge to a solution, but with a learning rate that is too high, our model may overshoot the solution and end up diverging from it. So feel free to experiment with different learning rates for your model. For our loss function, we'll be using sparse categorical cross entropy, and this is a loss function that works very well for classification problems where our classes are mutually exclusive. And in our example here, a person cannot be both eligible and not eligible for a loan. We'll also look at different types of loss functions and their applications in future videos. We also specify the metrics we'll use to evaluate our model during training, and we'll pick accuracy. Unlike the loss function, the metrics don't influence the model's training, but give us insights on how well the training process is going. To train our model, we'll call the fit method on the model, and this takes the training samples and the labels. We specify a validation split of 25%, and what this does is take 25% of our training data and creates a validation data set. A validation data set is a data set that the model will not train on, but will use to evaluate how well it performs on data it has not seen before. We also specify a batch size of 10, and this is the amount of data passed to the model at a time. So our samples will be grouped in batches of 10 for this training. We also specify 20 epochs, meaning that during the training process, the entire data set will be passed 20 times through the model. We set shuffle to be true so that our training data will be shuffled before training, and verbosity to be equal to 2. Verbosity is the amount of information that will be displayed during the training process, and specifying 2 in this example will show us the loss and accuracy of our model as we train it. Now after running model.fit, we'll see that with every epoch, our loss gradually decreases and the accuracy increases as our model converges to a solution. This is true for both the training and validation data set. However, we see that the model performs better on the training data than it does on the validation data. The performance of the validation data is still a bit high though, so our model is not overfitting. When a model overfits is when it performs very well on the training data and poorly on data it has not seen before. The last thing we'll do is generate another data set we'll use to test our model's predictions, and we'll do that in this cell. This data is generated the same way as our testing data, so we will not be explaining this cell since we've already seen how we pre-process our data. Instead, we'll move on to this cell. We'll run the predict method on our model, and our testing data will be passed to it. This method outputs an array of predictions, which really are just the activation outputs of the model's output layer nodes. When we print these predictions, we see that they are arrays of size 2, and the elements of these arrays are probabilities that a test samples fall under category A or B, with these categories representing groups of people that are eligible for a loan or not. That'll be all for this video. Thank you guys for watching. Leave a like if you found it helpful, and see you in the next one.